Imagine a force so pervasive, so quietly influential, that it shapes the very fabric of our universe, yet remains entirely invisible to the naked eye. This unseen power is the magnetic field, a silent architect of the cosmos. It is a region in space where magnetic forces manifest, born from the simple movement of electric charges. Yet its influence is anything but simple. These fields are omnipresent, weaving a vast, interconnected web that stretches across the desolate emptiness of intergalactic space, sweeps through the majestic, spiraling arms of galaxies, and cloaks the stars, planets, and even the enigmatic black holes that populate our universe. Though we cannot see them, their presence is undeniable, their effects profound. They are the gentle hand that guides the birth of stars, the powerful current that steers high-energy cosmic rays, and the invisible shield that protects worlds like our own from the relentless fury of their suns. From the smallest molecular clouds where new stars are forged, to the largest clusters of galaxies bound together by gravity, magnetic fields are the unseen wiring of the cosmos. The silent, omnipresent force that brings order to chaos and sculpts the grand cosmic tapestry we are only just beginning to comprehend. To understand these fields is to peel back a layer of reality, to glimpse the invisible architecture that underpins all of existence. This invisible architecture is not an abstract, distant phenomenon. It is a force that is intimately connected to our own existence, a silent guardian that makes life on Earth possible. Our planet is a magnetic world, a giant, spinning dynamo that generates a powerful magnetic field extending far out into space, creating a protective bubble known as the magnetosphere. This field is not a static entity. It is a dynamic, ever-changing shield, born from the churning, convective motions of molten iron and nickel deep within the Earth's outer core. This process, known as the geodynamo, transforms the planet's rotational and thermal energy into a vast, planetary-scale magnetic field. A field that is as essential to our survival as the air we breathe and the water we drink. The sun, our life-giving star, is a source of constant and often violent activity. It continuously emits a stream of charged particles, protons, and electrons known as the solar wind. This wind travels outwards through the solar system at hundreds of kilometers per second, a relentless supersonic gale that would, if left unchecked, strip away our planet's atmosphere over geological timescales, leaving us a barren and lifeless rock, much like our celestial neighbor, Mars. But Earth's magnetic field stands as a silent sentinel against this cosmic onslaught. The magnetosphere deflects the vast majority of the solar wind particles, forcing them to flow around our planet like water around a boulder in a stream. This constant, invisible battle in the space around our planet is what preserves our fragile atmosphere, protecting the delicate conditions that have allowed for the evolution and flourishing of life. We owe our very existence to this invisible magnetic shield. But the interaction between Earth's magnetic field and the solar wind is not just a story of protection. It is also a source of breathtaking beauty. Occasionally, some of the charged particles from the solar wind are trapped by the magnetosphere and are funneled down along the magnetic field lines towards the Earth's polar regions. As these high-energy particles collide with the atoms and molecules of our upper atmosphere, primarily oxygen and nitrogen, they excite them, causing them to glow. The result is one of nature's most spectacular displays, the aurora borealis in the north, and the aurora australis in the south. These dancing, shimmering curtains of green, pink, and violet light are a stunning, visible manifestation of the invisible forces that govern our planet's interaction with the sun. They are a breathtaking reminder that we live within a dynamic electromagnetic environment, and that the universe, even in its most violent aspects, can create moments of profound and ethereal beauty. The auroras are the poetry of planetary physics, a silent symphony played out in the polar skies, a testament to the power and the elegance of the magnetic field that keeps our world alive. The story of planetary magnetic fields is a story of diversity. When we look at our solar system, we see a veritable zoo of different magnetic worlds, each telling a unique story of its own internal dynamics and its evolutionary history. Jupiter, the king of the planets, boasts the most powerful magnetic field in our solar system, a field that is nearly 20,000 times stronger than Earth's. This immense field is not generated by molten iron, but by a vast, deep ocean of metallic hydrogen, a strange, exotic state of matter that is formed under the crushing pressures of Jupiter's interior. This mighty magnetosphere creates intense radiation belts that are a serious hazard for any spacecraft that ventures too close, and it drives spectacular, planet-sized auroras at Jupiter's poles. It even has a profound influence on its moons, like the volcanically active Io, whose fiery eruptions are thought to be, in part, fueled by the intense magnetic and electrical interactions with its parent planet. Mars, on the other hand, tells a more cautionary tale. Today, Mars has no global magnetic field to speak of. It has only localized, remnant patches of crustal magnetism, fossilized magnetic fields that are locked into the ancient rocks of its crust. These are the ghosts of a magnetic field that Mars likely had in its distant past, when its core was still hot and molten. The loss of this global magnetic field, which probably shut down billions of years ago as the planet's core cooled and solidified, had catastrophic consequences. Without a magnetosphere to protect it, the solar wind has, over eons, stripped away the vast majority of Mars's once thicker atmosphere, transforming it from a world that may have once been warm and wet into the cold, dry, and barren desert we see today. Venus, Earth's twin in size and composition, presents another puzzle. Despite its similar size, Venus has no significant, internally generated magnetic field. This is likely due to its incredibly slow rotation. A day on Venus is longer than its year, which is not fast enough to drive the necessary churning motions in its core to create a dynamo. The study of these different planetary magnetic fields is a form of comparative planetology that allows us to understand the key ingredients necessary for creating and sustaining a habitable world. It tells us that a planet's magnetic field is not just a geological curiosity. It is a crucial component of its climate, its atmosphere, and its ultimate potential to harbor life. The Earth's magnetic field is not a static, unchanging entity. The geological record, preserved in the magnetic minerals of ancient lava flows, tells us a remarkable story. Our planet's magnetic field has, throughout its history, repeatedly and dramatically flipped its polarity. The North Magnetic Pole has become the South Magnetic Pole, and vice versa. These geomagnetic reversals are not instantaneous events. They are complex and often chaotic, processes that can take several thousand years to complete. During a reversal, the main dipole component of the Earth's field weakens significantly, and the field can become much more complex, with multiple temporary north and south poles scattered across the globe. The exact mechanism behind these reversals is still a subject of active research, but it is thought to be related to the complex, turbulent dynamics of the molten iron in the Earth's outer core. The geodynamo is not a steady, clockwork machine. It is a chaotic system. And like all chaotic systems, it is subject to sudden and dramatic shifts in its behavior. The last major reversal occurred about 780,000 years ago, and there is some evidence to suggest that we may be in the early stages of a new one, as the strength of the Earth's magnetic field has been observed to be decreasing over the last few centuries, and the North Magnetic Pole is currently wandering across the Arctic at a surprisingly rapid rate. The prospect of a geomagnetic reversal can sound alarming. What would happen to our technological civilization, so dependent on satellites and power grids, if our planet's magnetic shield were to weaken significantly for a few thousand years? And what would be the impact on life? The fossil record does not show any clear evidence of mass extinctions being correlated with past reversals, which suggests that the consequences may not be as catastrophic as one might imagine. Even during a reversal, the Earth is not left completely unprotected. A weaker, more complex magnetic field would still provide some shielding from the solar wind, and our atmosphere itself is a powerful secondary shield against cosmic radiation. But there would undoubtedly be challenges. The increased influx of energetic particles could pose a risk to our technological infrastructure and could lead to more frequent and spectacular auroral displays at lower latitudes. The study of geomagnetic reversals is a powerful reminder of the dynamic and sometimes unpredictable nature of our own planet. It is a story that is written in the rocks beneath our feet, a story of a planet that is constantly changing, constantly evolving, a story whose next chapter we may be living through right now. The journey into the heart of magnetism takes us from the familiar shield of our own planet to the grand cosmic forges where stars themselves are born. The Sun, the star at the center of our solar system, is a magnetic powerhouse. Its magnetic field is generated by a complex dynamo process, similar to Earth's, but driven by the turbulent, convective motions of the hot ionized gas, or plasma, that makes up its interior. This solar dynamo is not a steady process. It is a cyclical one, with the Sun's overall magnetic field flipping its polarity approximately every 11 years. This 11-year cycle is the driving force behind all of solar activity. The Sun's magnetic field is not a simple bar magnet-like dipole. It is a complex, twisted and ever-changing web of magnetic flux tubes that are constantly being stretched, sheared, and tangled by the Sun's differential rotation, the fact that its equator rotates faster than its poles. When these tangled magnetic field lines become too stressed, they can suddenly snap and reconnect, releasing a tremendous amount of energy in a violent, explosive event. These are solar flares, some of the most powerful explosions in our solar system. A large solar flare can release the energy equivalent of millions of hydrogen bombs in a matter of minutes, sending a burst of high-energy radiation and charged particles out into space. Sometimes, these magnetic reconnection events can also trigger a coronal mass ejection, a vast billion-ton cloud of magnetized plasma that is hurled out from the Sun's atmosphere at millions of kilometers per hour. If a CME is directed towards Earth, it can have a significant impact on our planet's magnetic environment, triggering powerful geomagnetic storms, beautiful auroral displays, and potentially disrupting our satellites, power grids, and communication systems. The dark, cooler regions we see on the Sun's surface, known as sunspots, are also a magnetic phenomenon. They are areas where intense, concentrated magnetic field lines are poking through the Sun's visible surface, inhibiting the flow of hot gas from the interior and causing the region to cool down. The number of sunspots on the Sun varies in a cyclical way, reaching a maximum every 11 years, in sync with the solar magnetic cycle. The study of the Sun's magnetic field is not just an academic exercise, it is a matter of practical importance, as space weather can have a real and sometimes disruptive impact on our technological society. But to truly understand the cosmic role of magnetism, we must journey even further out, into the vast, cold, and dark molecular clouds that are the stellar nurseries of our galaxy. It is here, in these seemingly serene and quiescent clouds of gas and dust, that magnetic fields play their most crucial and creative role as the silent and often unacknowledged midwives of star formation. The birth of a star begins with the slow gravitational collapse of a dense core within a molecular cloud. But this collapse is not a simple, unimpeded freefall. It is a complex and delicate dance between the inward pull of gravity and the outward push of other forces. And the most important of these is the magnetic field that threads through the cloud. The interstellar medium is not empty. It is filled with a weak, but pervasive, magnetic field. As a cloud of gas collapses under its own gravity, it pulls these magnetic field lines in with it, compressing and amplifying them. This creates a magnetic pressure that can resist the gravitational collapse, slowing it down and regulating the process. Without the moderating influence of magnetic fields, the gravitational collapse of a molecular cloud would be a much more rapid and chaotic affair, likely leading to the formation of a few very massive stars, rather than the rich diversity of stellar masses that we actually observe. The magnetic field acts as a kind of cosmic brake, ensuring that star formation is a slow, steady, and relatively efficient process. But the magnetic field does more than just resist the collapse. It also plays a crucial role in solving one of the key puzzles of star formation, the angular momentum problem. A collapsing cloud of gas, due to the conservation of angular momentum, should spin faster and faster as it shrinks, in the same way that an ice skater spins faster when she pulls her arms in. The amount of angular momentum in a typical molecular cloud core is so large that, if it were all conserved in the final star, the star would be spinning so fast that it would tear itself apart. Something must be getting rid of the excess angular momentum, and that something is the magnetic field. The magnetic field lines that are threaded through the collapsing core are also connected to the surrounding, more diffuse gas of the cloud. As the core spins up, it twists these magnetic field lines, creating a magnetic torque that transfers the angular momentum outwards from the rapidly spinning core to the more slowly rotating envelope. This process, known as magnetic braking, is incredibly efficient, and it is what allows the protostar to shed its excess angular momentum and to continue its slow, steady collapse into a stable, newly formed star. The influence of magnetism on the star formation process is visible in the very structure of the stellar nurseries themselves. High-resolution images of molecular clouds, particularly those taken in polarized light, reveal a stunning filamentary structure. These are not random, chaotic tendrils of gas. They are ordered, coherent structures, vast magnetic rivers that are shaped and confined by the interstellar magnetic field. The gas in these filaments is thought to be flowing along the magnetic field lines, channeling material from the diffuse, outer regions of the cloud into the dense, star-forming cores. The magnetic field acts as a cosmic scaffolding, guiding the flow of matter and providing the architectural blueprint for the entire star formation process. But the relationship between magnetism and the cloud is a complex one. While the magnetic field can channel the flow of the ionized component of the gas, the neutral component can, over long timescales, slowly drift across the magnetic field lines in a process known as ambipolar diffusion. This is a crucial step in the formation of a star, as it allows a dense core to decouple from the magnetic support of the larger cloud and to begin its final, inexorable gravitational collapse. The star formation process is a delicate interplay between the inward pull of gravity, the outward push of magnetic pressure, and the slow, patient drift of neutral matter through the magnetic web. The observational tools we use to study this invisible magnetic architecture are becoming increasingly powerful. By measuring the polarization of the faint, thermal radiation emitted by dust grains in molecular clouds, we can map the orientation of the magnetic field lines, as the elongated dust grains tend to align themselves with the local field. The Zeeman effect, the splitting of spectral lines in the presence of a magnetic field, provides a more direct, but much more challenging, way to measure the strength of the field itself. With new powerful telescopes like the Atacama Large Millimeter/Submillimeter Array, We are now able to create stunning, high-resolution maps of the magnetic fields in nearby star-forming regions, providing a detailed, empirical check on our theoretical models. These observations are confirming the central and often dominant role of magnetism in the birth of stars. They are showing us a universe where the process of creation is not a simple matter of gravity, but a complex and beautiful dance between gravity, turbulence, and the silent, guiding hand of the magnetic field. The journey into the heart of cosmic magnetism takes us from the relatively gentle, organizing influence of the fields in stellar nurseries to the far more violent and spectacular realm of cosmic jets. These are some of the most powerful and enigmatic phenomena in the universe, narrow, highly collimated beams of plasma that are ejected from the vicinity of massive celestial objects at speeds approaching the speed of light. They are cosmic fire hoses of incredible power, capable of traveling for hundreds of thousands and even millions of light years, shaping the galaxies and the intergalactic medium through which they pass. And at the heart of every cosmic jet lies a powerful, twisted, and dynamic magnetic field. The formation of these jets is intimately tied to the process of accretion, the spiraling inflow of gas and dust onto a central, compact object. This can be a young, newly forming star, a dense, stellar remnant like a neutron star or a white dwarf, or, in the most spectacular cases, a supermassive black hole at the center of a galaxy. As this material spirals inwards, it forms a hot, dense, and rapidly rotating accretion disk, and it is from the inner regions of this chaotic, swirling maelstrom of plasma that the jets are born. The magnetic field is the key ingredient that channels and accelerates this outflow. The rapid rotation of the accretion disk, combined with the turbulent, convective motions within it, acts as a powerful dynamo, amplifying and twisting the magnetic field lines into a tightly wound, helical structure that extends outwards, perpendicular to the disk. These twisted, magnetic field lines act like a cosmic nozzle, a magnetic slingshot that grabs onto the charged particles of the plasma and flings them outwards at incredible speeds. The process of magnetic reconnection, where stressed and twisted magnetic field lines can suddenly snap and reconfigure themselves, is thought to be a key mechanism for releasing the immense amounts of energy that power these jets. The high-energy particles within the jets, spiraling around these powerful magnetic field lines, emit a strong, characteristic form of radiation known as synchrotron radiation. This radiation, which is most prominent at radio wavelengths, is the smoking gun signature of a cosmic jet, and it is what allows us to map their structure and to study their properties across the vast distances of the cosmos. The most powerful jets in the universe are those that are launched from the accretion disks around supermassive black holes at the centers of active galaxies. These are the quasars and radio galaxies, some of the most luminous objects in the cosmos. Their jets can be truly colossal, extending far beyond the confines of their host galaxy and plowing into the tenuous, hot gas of the intergalactic medium. As they do so, they create vast, expanding lobes of radio-emitting plasma, giant structures that can be hundreds of thousands of light years across. These jets have a profound and transformative impact on their environment. The immense amount of energy and momentum they carry can heat up the surrounding gas, preventing it from cooling and forming new stars. This jet feedback is now thought to be a crucial mechanism in regulating the growth of massive galaxies, explaining why the most massive galaxies in the universe seem to have stopped forming stars billions of years ago. The jets from their central, supermassive black holes have effectively sterilized them, cutting off their supply of cold, star-forming gas. But jets are not just found in the most massive and exotic systems. We also see them on a much smaller scale, associated with the birth of ordinary sun-like stars. These protostellar jets, often referred to as Herbig-Haro objects, are a crucial part of the star formation process. They are thought to be the primary mechanism by which a young upforming star sheds its excess angular momentum, allowing it to continue its gravitational collapse. The outflowing jet carries away the spin, allowing the central protostar to continue to grow in mass. The study of cosmic jets is a field that brings together many different areas of astrophysics, from plasma physics and magnetohydrodynamics to general relativity and high-energy particle physics, and our observational tools are becoming increasingly powerful. With arrays of radio telescopes like the Very Large Array and the Future Square Kilometer Array, we can create stunning, high-resolution images of the jets and their interaction with their environment. With X-ray and gamma-ray telescopes in space, we can study the high-energy particles within the jets and the processes that accelerate them to near the speed of light. And with the Event Horizon Telescope, a global network of radio telescopes that can achieve an angular resolution equivalent to seeing an orange on the surface of the moon. We are now able to image the very base of the jet, right at the edge of the event horizon of a supermassive black hole. These observations are providing us with an unprecedented view of one of nature's most extreme and powerful phenomena, a phenomenon that is driven, at its core, by the beautiful, complex, and violent dance of matter and magnetism in the heart of the cosmos. The universe is a gallery of extremes, and nowhere is this more apparent than in the dense, crushed remnants of dead stars. It is in these stellar graveyards that magnetic fields can reach strengths that are almost beyond our comprehension, creating some of the most exotic and fascinating objects in the cosmos. A white dwarf is the final, evolutionary state of a star like our Sun after it has exhausted its nuclear fuel. It sheds its outer layers to form a beautiful, glowing planetary nebula, leaving behind a hot, dense core of carbon and oxygen, about the size of the Earth, but with the mass of the Sun. Many white dwarfs have surprisingly strong magnetic fields, ranging from thousands to even billions of times the strength of Earth's magnetic field. These fields are thought to be a fossilized remnant of the magnetic field of the progenitor star, compressed and amplified during the star's collapse. These strong fields have a profound effect on the white dwarf's atmosphere, distorting the energy levels of the atoms and creating a unique and very complex spectral signature, a phenomenon known as the Zeeman effect. By carefully analyzing this spectral splitting, astronomers can map the strength and structure of the magnetic fields on the surfaces of these dead stars. But the story of magnetic compact objects gets even more extreme when we consider the fate of more massive stars. A star that is several times more massive than the Sun will end its life in a spectacular supernova explosion, its core collapsing under its own immense gravity to form a neutron star. These are objects of incredible density, packing more than the mass of the Sun into a sphere that is only about 20 kilometers in diameter. A single teaspoon of neutron star material would weigh billions of tons. As the core collapses, the conservation of angular momentum causes the neutron star to spin incredibly rapidly, often hundreds of times per second. And the conservation of magnetic flux causes its magnetic field to be amplified to truly staggering levels, typically around 1 trillion times the strength of Earth's field. If the neutron star's magnetic axis is misaligned with its rotation axis, it will sweep a powerful beam of electromagnetic radiation across space, like a cosmic lighthouse. If this beam happens to sweep across the Earth, we see it as a regular, pulsating signal, and we call the object a pulsar. Pulsars are some of the most precise clocks in the universe, and they are powerful probes of the interstellar medium and of the laws of gravity in extreme conditions. But the real drama unfolds when these magnetic, compact objects are not alone, but are part of a binary star system. If a white dwarf or a neutron star is in a close orbit with a normal companion star, its powerful gravity can pull material from the companion, creating an accretion disk of hot, spiraling gas. The interaction between this infalling material and the magnetic field of the compact object creates some of the most energetic and dynamic phenomena in the universe, in a system known as a magnetic cataclysmic variable. The magnetic field of the white dwarf is so strong that it prevents the formation of a normal accretion disk. Instead, the infalling material is channeled directly along the magnetic field lines, forming a stream or an accretion column that crashes onto the magnetic poles of the white dwarf, creating an intensely hot X-ray emitting shock. In binary systems containing a neutron star, the infalling material can accumulate on the surface, its temperature and density increasing until it triggers a runaway thermonuclear explosion, a powerful burst of X-rays that can be seen across the galaxy. But the most extreme magnetic objects in the universe are the magnetars. These are a rare and still not fully understood type of neutron star with magnetic fields that are up to 1,000 times stronger than those of a typical pulsar, reaching strengths of up to 1,000,000,000 times that of the Earth. These are the strongest magnetic fields known to exist in the cosmos. The energy stored in these immense fields is so great that it can cause the solid crust of the neutron star to crack and shift in a violent starquake. These starquakes can trigger a catastrophic release of magnetic energy, creating a giant flare, a burst of gamma rays and X-rays that can, for a brief moment, outshine all the other sources in our galaxy combined. A giant flare from a magnetar in our own galaxy, if it were directed towards us, could have a significant impact on the Earth's upper atmosphere, even from a distance of tens of thousands of light years. Magnetars are also thought to be a leading candidate for the source of the enigmatic fast radio bursts, the powerful millisecond-long bursts of radio waves that are being detected from distant galaxies, the extreme and often violent. Behavior of these magnetic compact objects is a powerful testament to the central role that magnetism plays in the high-energy universe. They are natural laboratories for studying the behavior of matter and energy under conditions of extreme density, gravity, and magnetism, conditions that we can never hope to replicate on Earth, and they are a reminder that the universe is full of objects that are far stranger, more powerful, and more beautiful than our classical intuition could have ever imagined. Magnetars are the undisputed kings of cosmic magnetism, a rare and enigmatic class of neutron star whose magnetic fields are so titanically powerful that they warp the very fabric of reality around them. Born from the fiery death of massive stars in supernova explosions, these objects are a testament to the extremes that nature can achieve. The process of their formation is a lesson in the conservation laws of physics. As the core of a massive star collapses under its own gravity, from a size of hundreds of thousands of kilometers down to a sphere just 20 kilometers across, it conserves its angular momentum, causing it to spin up to incredible speeds, and it conserves its magnetic flux, compressing the magnetic field of the progenitor star to unimaginable densities. While all neutron stars are highly magnetized, it is thought that only those that are born with a particularly rapid initial spin can drive a powerful enough dynamo mechanism in their turbulent, convective interiors to amplify the magnetic field to the quadrillion Gauss levels that define a magnetar. This is a field that is 1,000 times stronger than that of a typical pulsar, and 1,000 trillion times stronger than the magnetic field of our own Earth. A magnetic field of this magnitude is so strong that it has profound and bizarre effects on the physics in its vicinity. It would distort the very shape of the atoms on the magnetar's surface, stretching them into long, thin needles aligned with the field lines. It would cause the vacuum of space itself to become birefringent, a quantum electrodynamical effect where the vacuum acts like a crystal, splitting a beam of light into two different polarizations. And it is the primary source of the magnetar's own extraordinary energy output, Unlike a normal pulsar, which is powered by its rotational energy, a magnetar is powered by the decay of its immense magnetic field. The energy stored in this field is so vast that it can cause the solid, crystalline crust of the neutron star to periodically crack and buckle, in a violent event known as a starquake. This is analogous to an earthquake on Earth, but on a scale of energy and violence that is almost beyond comprehension. These starquakes can trigger a catastrophic and sudden reconfiguration of the external magnetic field, leading to a giant flare, a burst of high-energy gamma rays and X-rays that can release more energy in a fraction of a second than our Sun will emit in 100,000 years. In 2004, a giant flare from the magnetar SGR 1806-20, located about 50,000 light-years away on the other side of our galaxy, was so powerful that it measurably disturbed the Earth's ionosphere. If such an event were to occur from a magnetar much closer to us, the consequences could be significant. The intense and often violent activity of magnetars also explains their relatively short, observable lifetimes. The decay of their magnetic field, which powers their outbursts, also causes them to spin down much more rapidly than a normal pulsar. A typical magnetar will slow its rotation from milliseconds to several seconds in just a few thousand years. After about 10,000 years, its magnetic field has likely decayed to a point where it is no longer active, and the magnetar becomes a quiescent and largely invisible neutron star. This short lifetime is one of the reasons why magnetars are so rare. We can only see them during the brief and spectacular period of their youthful activity. The study of these extreme objects has been revolutionized by our high-energy telescopes in space, like the Chandra X-ray Observatory and the Neil Gehrels Swift Observatory. These instruments are able to detect the frequent, smaller bursts and the rare, giant flares from magnetars, allowing us to study the dynamics of their magnetic fields and the physics of their violent outbursts. These observations are providing crucial data to test our theoretical models of magnetar physics, and they are also shedding light on one of the most exciting new mysteries in astronomy, the origin of fast radio bursts. FRBs are intense, millisecond-long bursts of radio waves that are being detected from distant, extragalactic sources. Their origin is unknown, but a leading candidate is a young active magnetar. In 2020, a powerful radio burst, with properties very similar to an FRB, was detected from a magnetar within our own Milky Way galaxy, providing the first, strong, smoking gun evidence for this connection. It seems likely that at least some, and perhaps all, FRBs are the extragalactic cousins of the giant flares we see from the magnetars in our own cosmic backyard. Magnetars are more than just astronomical curiosities. They are natural laboratories for probing the limits of physics. Their immense magnetic fields allow us to study the behavior of matter and radiation under conditions of extreme energy and density, conditions that are far beyond anything we can ever hope to create on Earth. They are a window into the world of quantum electrodynamics in the strong field regime, where the vacuum itself becomes a dynamic, physical medium, and they are a powerful reminder that the universe is a place of constant and often violent transformation, a place where the death of a star can give birth to an object of such extreme and beautiful strangeness that it challenges the very boundaries of our scientific understanding. The centers of galaxies are the cosmic crucibles where the most extreme forces of nature are at play. And at the very heart of most, if not all, large galaxies lies a supermassive black hole, a gravitational behemoth with a mass of millions, or even billions, of times that of our Sun. These objects are not just passive gravitational sinks, they are dynamic, powerful engines that can have a profound and transformative impact on the evolution of their entire host galaxy. And the key to unlocking their power, the medium through which they exert their influence, is the magnetic field. A supermassive black hole, on its own, is a relatively simple object, described only by its mass and its spin. The real action happens in the accretion disk that often surrounds it, a swirling, chaotic vortex of gas, dust, and shredded stars that are being pulled in by the black hole's immense gravity. As this material spirals inwards, it is heated to millions of degrees by friction, creating an intensely luminous source of radiation that can, in the case of a quasar, outshine all the stars in the host galaxy combined. And this accretion disk is a magnetic cauldron. The turbulent, churning motions of the hot, ionized plasma in the disk act as a powerful dynamo, amplifying and tangling the magnetic field lines, creating a complex and dynamic magnetic structure that is intimately tied to the process of accretion itself. It is this magnetic field that is thought to be the primary mechanism for launching the spectacular relativistic jets that we see emerging from the centers of many active galaxies. In a process that is still not fully understood, but is likely related to the twisting of magnetic field lines by the rotating accretion disk and the spinning black hole itself, a portion of the infalling material can be grabbed by the magnetic field and accelerated outwards, perpendicular to the disk, at speeds approaching the speed of light. The Blandford-Zajac mechanism is a leading theoretical model for how this can happen. It proposes that the rotational energy of the spinning black hole itself can be extracted by the magnetic field lines that thread its event horizon, providing a powerful source of energy to drive the jets. In this picture, the magnetic field is a kind of cosmic transmission belt, converting the gravitational and rotational energy of the black hole system into the kinetic energy of a powerful, collimated outflow. We are now, for the first time in history, able to image the immediate vicinity of a supermassive black hole and to directly map the structure of its magnetic field. The Event Horizon Telescope, a global network of radio telescopes that uses a technique called very long baseline interferometry to create a virtual, Earth-sized telescope, has produced stunning images of the shadow of the supermassive black holes at the center of our own Milky Way galaxy and the giant elliptical galaxy M87. And by measuring the polarization of the radio waves emitted by the hot plasma around the black hole, the EHT has been able to create the first ever maps of the magnetic field structure right at the edge of the event horizon. These images have revealed a swirling, ordered pattern of magnetic field lines, confirming the theoretical predictions and providing a stunning, direct view of the magnetic engine that is thought to be responsible for launching the M87 jet. The influence of these black hole-driven, magnetized jets extends far beyond the galactic nucleus. They are a powerful form of feedback, a mechanism by which the central black hole can regulate the growth of its entire host galaxy. The jets plow into the interstellar medium of the galaxy, creating vast, expanding bubbles of hot gas and driving powerful shock waves that can heat up the surrounding cooler gas. This can have a profound effect on the process of star formation. Stars are born from the collapse of cold, dense molecular clouds. If the gas in a galaxy is heated up by the energy injected from a central jet, it can be prevented from cooling and collapsing, effectively shutting down or quenching the process of star formation. This jet mode feedback is now thought to be one of the key reasons why the most massive galaxies in the universe are no longer forming stars. They are red and dead, their star formation having been quenched billions of years ago by the powerful and ongoing activity of their central, supermassive black holes. The magnetic field is the crucial ingredient in this process, as it is what allows the energy and momentum of the jet to be efficiently coupled to the surrounding gas. The interplay between the growth of a supermassive black hole and the evolution of its host galaxy is one of the most active and exciting areas of modern astrophysics. It is a story of coevolution, of a deep and intimate connection between the smallest and the largest scales of a galaxy. And it is a story that is, at its heart, a magnetic one. The magnetic fields in the accretion disk launch the jets. The jets regulate the star formation in the galaxy. The star formation provides the fuel that feeds the black hole, and the cycle continues. It is a beautiful, self-regulating cosmic ecosystem, a dance of gravity, gas, and magnetism that has shaped the appearance and the history of every large galaxy in the universe. Our own Milky Way is a relatively quiet galaxy at present, its central black hole in a state of slumber, but it has likely gone through more active jet-producing phases in its past, and it will likely do so again in the future. The study of the magnetic fields around black holes is not just about understanding these exotic, extreme objects. It is about understanding the grand, cosmic story of which we are a part. The story of how galaxies and the stars and planets within them are born, how they live, and how they die. The influence of magnetism is not confined to the dense, active environments of stars and galaxies. It extends out into the vast, tenuous, and seemingly empty spaces between them. The universe, on its largest scales, is structured as a cosmic web, an intricate, interconnected network of vast filaments of galaxies and dark matter, separated in immense, almost empty voids. And this cosmic web is not just a gravitational structure, it is a magnetized one. The space between the galaxies, the intergalactic medium, is permeated by a weak but pervasive magnetic field. The existence of these intergalactic magnetic fields is a profound and puzzling discovery. Their strength is incredibly small, typically 1 billion times weaker than the magnetic field of the Earth, but they extend over millions, and even billions, of light years, making them the largest coherent magnetic structures in the universe. The origin of these cosmic-scale magnetic fields is one of the great unsolved mysteries of modern cosmology. Where did they come from? One possibility is that they are of astrophysical origin, that they were seeded by the magnetic fields that were generated within the first stars and galaxies and then ejected into the intergalactic medium by powerful galactic winds. Outflows of gas driven by supernova explosions and the activity of central black holes over cosmic time. These ejected fields would have been stretched and sheared by the large-scale flows of the expanding universe, eventually filling the vast spaces of the cosmic web. Another, more exotic, possibility is that they are of primordial origin, that they were created in the very early universe, long before the first stars and galaxies ever formed. There are several proposed mechanisms for how this could have happened. During the period of cosmic inflation, quantum fluctuations in the electromagnetic field could have been stretched to cosmological scales, creating a primordial magnetic field. Or, during one of the phase transitions of the early universe, such as the electroweak transition or the QCD transition, bubbles of a new vacuum state could have formed, and the collisions between these bubbles could have generated magnetic fields. Distinguishing between these astrophysical and primordial origin scenarios is a major goal of modern cosmology. A primordial magnetic field would have a different statistical signature than one that was generated later, and this could, in principle, be detected in the subtle patterns of the cosmic microwave background or in the large-scale distribution of galaxies. The detection of a primordial magnetic field would be a discovery of monumental importance, as it would provide a direct window into the physics of the universe in its first fleeting moments. Within the dense, hot environments of galaxy clusters, the largest gravitationally bound structures in the universe, the magnetic fields are significantly stronger than in the general intergalactic medium, reaching strengths of a few microgauss, similar to the field in our own Milky Way. These intracluster magnetic fields are thought to be amplified by the turbulent, churning motions of the hot X-ray emitting gas that fills the space between the cluster galaxies. The constant motion and merging of galaxies within the cluster acts as a powerful, large-scale dynamo, tangling and amplifying the magnetic field lines. These cluster magnetic fields play a crucial role in the physics of the intracluster medium. They can influence the transport of heat, potentially solving the long-standing cooling flow problem. The mystery of why the gas in the centers of many clusters is not cooling and forming stars as rapidly as simple models would predict. They can also accelerate cosmic ray particles to incredible energies, creating the vast, diffuse radio halos and relics that are observed in many galaxy clusters. The study of these cosmic-scale magnetic fields is incredibly challenging. They are too weak to be detected directly. Instead, we must rely on indirect methods. The most powerful of these is Faraday rotation. When a beam of polarized light, such as the radio waves from a distant quasar, passes through a magnetized plasma, its plane of polarization is rotated. The amount of this rotation depends on the strength and orientation of the magnetic field along the line of sight. By observing the Faraday rotation of many background sources seen through a galaxy cluster or a filament of the cosmic web, astronomers can create detailed, three-dimensional maps of the magnetic field structure. The next generation of radio telescopes, particularly the square-kilometer array, will revolutionize this field. With its unprecedented sensitivity and its ability to survey vast areas of the sky, the SKA will be able to map the cosmic magnetic web with a detail and a depth that is currently unimaginable. It will allow us to trace the magnetic fields from the hearts of galaxies out into the intracluster medium and along the vast filamentary structures that connect them. This will provide a completely new and fundamentally important view of the universe. It will transform our understanding of the cosmic web from a simple, gravitational structure into a dynamic, magnetized ecosystem, a place where the flow of matter and energy is governed by the complex and beautiful interplay between gravity and magnetism. The invisible, magnetic threads of the cosmos are what bind it together, and we are, for the first time, beginning to learn how to see them. The study of cosmic magnetism is a field that is driven by a constant and creative interplay between theoretical modeling, numerical simulation, and observational astronomy. Because magnetic fields are invisible, we must rely on a variety of clever, indirect techniques to detect their presence and to map their structure. One of the most important of these, as we have seen, is the observation of synchrotron radiation. When a high-energy charged particle, like an electron, spirals around a magnetic field line at a speed close to the speed of light, it emits a powerful beam of electromagnetic radiation. This synchrotron emission is a characteristic fingerprint of a magnetized, high-energy environment, and it is most prominent at radio wavelengths. By creating detailed, high-resolution maps of the synchrotron emission from objects like supernova remnants, radio galaxies, and galaxy clusters, radio astronomers can trace the structure of the magnetic fields and study the properties of the high-energy particles within them. The polarization of this synchrotron light provides even more information, as it is directly related to the orientation of the magnetic field lines. To carry out these observations, astronomers use some of the most powerful and sophisticated telescopes on Earth, ground-based radio interferometers, like the Very Large Array in New Mexico and the Low Frequency Array in Europe, consist of many individual radio antennas spread out over large distances. By combining the signals from these antennas, they can achieve an angular resolution that is equivalent to a single telescope many kilometers in size, allowing them to create incredibly detailed images of the radio sky. In the millimeter and submillimeter part of the spectrum, the Atacama Large Millimeter Submillimeter Array in Chile A powerful interferometer situated high in the Andes Mountains has revolutionized our view of the cold, dusty universe where stars and planets are born. ALMA's stunning images of protoplanetary disks and molecular clouds have revealed the intricate, filamentary structures that are shaped by magnetic fields, providing a direct view of the magnetic architecture of star formation. But the future of radio astronomy and of cosmic magnetism research lies with the Square Kilometer Array. This is not a single telescope, but a next-generation global observatory. A network of thousands of radio dishes and millions of low-frequency antennas that will be spread across 2 continents, in South Africa and Australia. When completed, the SKA will be the largest and most sensitive radio telescope ever built. It will have a collecting area of a square kilometer, and it will be able to survey the sky thousands of times faster than any existing instrument. The SKA will be a magnetic field machine. Its unprecedented sensitivity will allow it to detect the faint, polarized signals from the most distant galaxies, providing a map of how the magnetic fields in galaxies have evolved over cosmic time. It will be able to map the Faraday rotation of thousands of background sources, creating a 3-dimensional tomographic map of the magnetic field in the cosmic web itself, allowing us to test our theories of the origin of cosmic magnetism. And it will be a powerful tool for studying transient magnetic phenomena, like fast radio bursts and the mergers of neutron stars.
Imagine that you are floating in space, where there is no up or down, only an infinite darkness dotted with lights. You feel a cold that is not just a lack of heat, but a profound emptiness, a presence of absolute nothing that seeps into the very idea of existence. Before you, something unimaginable emerges from this void, a planet with oceans of liquid diamonds and rain of pure iron. The universe holds worlds so strange that human imagination could never have conceived them. There are planets where a day lasts longer than a year, places where the atmosphere would crush you before you could scream. There are huge gas giants with storms raging for thousands of years, and worlds that resemble our Earth, at least at first glance, but are fundamentally, irrevocably alien. These distant worlds may hold the answer to the question of whether we are truly alone in the universe, or if we are just one note in a vast cosmic symphony. This journey begins not with a single planet, but in the cold, dark nurseries where all worlds are born. In the vast, silent gulfs between the stars, great clouds of interstellar gas and dust drift like cosmic ghosts. These are nebulae, and they are not empty voids, but the fertile grounds from which new worlds are born. These colossal structures, some spanning hundreds of light years, are the remnants of previous generations of stars. When massive stars reach the end of their lives, they explode in brilliant supernova, scattering the elements they forged in their nuclear hearts: carbon, oxygen, iron, all the building blocks of life and planets into the surrounding space. These elements enrich the primordial hydrogen and helium that have existed since the early moments of the universe, creating a complex chemical soup for millions of years. These clouds can drift in a delicate balance between the inward pull of their own gravity and the outward pressure from the heat of nearby stars and the subtle forces of their own internal motions. But this tranquility is not eternal. A disturbance, like the shockwave from another nearby supernova or the gravitational nudge from a passing star, can disrupt this balance, causing a region within the cloud to begin to collapse. As this dense core of gas and dust contracts under its own gravity, it begins to heat up and spin faster, conserving its angular momentum just as an ice skater spins faster when she pulls in her arms. At the center of this collapsing cloud, the material becomes so hot and dense that a protostar ignites, a stellar embryo not yet hot enough to begin nuclear fusion. It glows with a deep red light, its energy coming from the heat of gravitational contraction alone. Around this newborn protostar, a rotating disk of the remaining gas and dust forms, a structure known as a protoplanetary disk. This is the birthplace of planets. It is a cosmic potter's wheel, a swirling vortex of material from which new worlds will be sculpted over millions of years. This disk is not uniform. The intense heat from the young star creates a temperature gradient. In the inner regions of the disk, closer to the protostar, it is too hot for volatile substances like water, ammonia, and methane to condense into ice. Only materials with high melting points, such as metals like iron and nickel and rocky silicates, can survive. This region is known as the rock line. Further out, beyond a boundary called the snow line or frost line, the temperature is low enough for those volatile compounds to freeze into solid ice particles. This distinction is crucial for understanding the architecture of a planetary system. In the inner part of the disk, small dust particles, remnants of the initial cloud, begin to stick together through electrostatic forces, like dust bunnies forming under a bed. Over time, these small clumps grow into larger and larger objects through a process called accretion. They collide and merge, forming pebbles, then kilometer-sized rocks called planetesimals. These planetesimals are the building blocks of planets. Their own gravity becomes strong enough to attract more material, and through a chaotic series of collisions, they gradually sweep up the material in their orbits, growing into protoplanets, and finally, into full-fledged rocky planets like Mercury, Venus, Earth, and Mars. In the outer regions of the disk, beyond the snow line, the story is different. Not only are metals and rocks available, but there is also a vast reservoir of ice. This means there is much more solid material to work with, allowing for the formation of much larger planetary cores, perhaps 10 times the mass of Earth. Once these cores reach a critical mass, their gravity is so strong that they can begin to rapidly accrete the abundant hydrogen and helium gas from the surrounding disk. This process of runaway gas accretion forms the gas giants, like Jupiter and Saturn, and the ice giants, like Uranus and Neptune. These outer giants, in turn, have a profound influence on the entire system. Their immense gravity can sling planetesimals and comets around, some into the inner solar system, delivering water and organic molecules to the young rocky planets, and others out of the system entirely. However, each planetary system is unique, a product of the specific conditions of its birth and the chaotic dance of gravitational interactions that followed. Astronomers have discovered systems where giant planets, so-called hot Jupiters, orbit much closer to their star than Mercury does to the Sun, a configuration that was once thought to be impossible. These giants likely formed further out and then migrated inward, disrupting the orbits of any smaller planets in their path. We have found worlds that orbit 2 stars at once, and even planets that have been ejected from their systems and now wander through the cold darkness of interstellar space alone. The diversity of planets in our universe is astounding and constantly surprises us. Our own solar system is just one of many configurations that the universe creates, a particular outcome of a cosmic lottery played out over billions of years. And with every new telescope and every new method of observation, we discover more and more fascinating worlds waiting to be explored. These are not just distant points of light, they are the products of the same cosmic processes that created our own home, each with its own story, its own history, and its own potential. Closest to our sun orbits a small, scorched world that resembles a long-forgotten stone thrown into a fire. Mercury, named after the swift-footed messenger of the Roman gods, is the smallest planet in our solar system and also the fastest. It whips around the sun in just 88 Earth days, its velocity a constant battle against the star's immense gravitational pull. This planet is a world of extremes, a place of violent contrasts sculpted by its proximity to the solar furnace. During a single languid Mercurian day, which lasts approximately 176 Earth days, the temperatures on the sun-baked surface rise to a staggering 430 degrees Celsius, hot enough to melt lead and tin. But as the long night finally descends, with no substantial atmosphere to trap the heat, the temperature plummets to a cryogenic minus 180 degrees Celsius. This temperature swing of over 600 degrees is the most extreme of any planet in our solar system. If you were to walk on the surface of Mercury, you would see a landscape eerily similar to our moon, a desolate, ancient terrain pockmarked with countless craters, scars from billions of years of bombardment by asteroids and comets. The sky here is always a deep, star-filled black, because Mercury has only a tenuous exosphere, a thin veil of atoms blasted off its surface by the solar wind, far too thin to scatter sunlight. The sun would appear nearly 3 times larger in the sky than we see it from Earth, a blinding, terrifying orb whose unfiltered radiation would instantly burn you. But Mercury is not just a barren desert without interest. In one of the solar system's most beautiful paradoxes, at its poles, in the permanent shadows of deep craters where sunlight never reaches, there is water ice. On one of the hottest planets, you can find frozen water. This ice, confirmed by the Messenger spacecraft, could have been delivered there by cometary impacts over billions of years, or it could have been formed by chemical reactions involving hydrogen from the solar wind. These deposits of ice, protected from the sun's glare and eternal darkness, could be a vital resource for future human exploration. One of the strangest properties of Mercury is its rotation, which is locked in a unique 3-2 spin-orbit resonance. While it orbits the Sun in 88 days, it rotates on its axis exactly 3 times for every 2 orbits. This means that on Mercury, a solar day, the time from one sunrise to the next, lasts for 176 Earth days, which is exactly 2 Mercurian years. This peculiar dance with the Sun creates a bizarre visual effect. An observer on the surface would see the Sun rise, move across the sky, then appear to slow down, stop, move backward for a short time, and then resume its forward motion, a phenomenon known as a double sunrise. Scientists have also revealed that Mercury has an unusually large iron core, which takes up approximately 85% of the planet's volume. For comparison, Earth's iron core makes up only about 17% of its volume. This disproportionately large core suggests that Mercury may have suffered a cataclysmic event in its distant past. One theory proposes that a massive collision with another protoplanet stripped away much of its original rocky mantle, leaving behind the dense, iron-rich remnant we see today. Another idea is that the intense solar wind from a young, more active sun simply vaporized and blew away the lighter materials of its outer layers. This giant iron core is also responsible for Mercury's magnetic field. While much weaker than Earth's, it is still a puzzle. As a planet this small should have cooled and solidified its core long ago, shutting down the dynamo that generates a magnetic field. The existence of this field suggests that part of Mercury's core may still be molten. Despite its relative proximity to Earth, we know less about Mercury than about many more distant planets. Its exploration is difficult due to the Sun's intense gravity, which makes it hard for a spacecraft to enter into orbit, and its blinding glare, which complicates observation from terrestrial telescopes. So far, only 2 missions have visited it, Mariner 10 in the 1970s, which performed 3 brief flybys, and the Messenger probe, which orbited it from 2011 to 2015, mapping its surface and revealing many of its secrets. A new mission, Bepi Colombo, a joint venture between the European and Japanese space agencies, is currently on its way and will enter orbit in 2025, promising to unveil even more of the mysteries of this small, swift, and strange world. In the morning and evening hours, we can often observe a glittering point of light in the sky, a beacon so bright that people for millennia have called it the morning star or the evening star. Venus, named after the Roman goddess of love and beauty, is our closest planetary neighbor and in many ways resembles Earth. It has almost the same size, mass, and density as our planet. That is why it is often called Earth's sister, or its twin. But appearances are deceiving. While Earth is a blue oasis of life, a world of temperate climates and liquid oceans, Venus is a hellscape, a toxic inferno where a human would not survive for even a minute. Its atmosphere is a crushing 90 times denser than Earth's, composed almost entirely of carbon dioxide, which creates an extreme and more runaway greenhouse effect. The temperatures on the surface are a uniform 460 degrees Celsius, hotter than the surface of Mercury, despite being nearly twice as far from the Sun. It is hot enough to melt lead, and this temperature is constant across the entire planet, from the equator to the poles, day and night. On Venus, it constantly rains, but it is not a refreshing shower of water. The thick yellowish clouds that perpetually shroud the planet are made of sulfuric acid. These corrosive drops fall from the upper atmosphere but never reach the surface. They evaporate in the hellish heat of the lower atmosphere, creating a cycle of acid rain that never ends. If you could walk on the surface of Venus, you would see a dim, orange-tinted sky and a desolate landscape of vast volcanic plains and crumpled mountain ranges. The immense pressure of the atmosphere would crush you with the force of being a kilometer deep in Earth's oceans. The air is so thick that it behaves more like a fluid than a gas, and the landscape is scoured by slow but powerful winds. The surface of Venus is a testament to a violent volcanic past. It is covered in thousands of volcanoes, more than any other planet in the solar system, including massive shield volcanoes and strange, pancake-like domes formed by viscous lava. The entire surface appears to have been repaved by massive volcanic eruptions in a global cataclysm about 500 million years ago, an event that wiped out any earlier craters and reset the planet's geological clock. What is fascinating is that Venus rotates in the opposite direction to most of the planets in the solar system, a phenomenon known as retrograde rotation. And its rotation is incredibly slow. One day on Venus lasts for 243 Earth days, which is longer than its year, which has 225 Earth days. This means that on Venus, a day lasts longer than a year. The sun rises in the west and sets in the east, but a full day-night cycle takes more than a third of an Earth year. The reason for this slow, backward spin is a mystery. It may have been caused by a massive impact in its early history, or perhaps by the long-term effects of its thick atmosphere, creating tidal forces with the planet's solid body. But it was not always like this. Many scientists believe that Venus may have once been a much more hospitable place, a true sister to the early Earth. Billions of years ago, it may have had oceans of liquid water and a milder climate, potentially with conditions suitable for the emergence of life. So, what went wrong? The leading theory is that Venus was a victim of a runaway greenhouse effect. Being slightly closer to the sun, it received more solar radiation. As the young sun gradually increased its luminosity, the surface waters on Venus began to evaporate at an accelerated rate. Water vapor is a potent greenhouse gas. So, as more of it entered the atmosphere, the planet began to heat up even more. This, in turn, led to the evaporation of more water, creating a vicious feedback loop. Eventually, the oceans boiled away entirely. In the upper atmosphere, the intense ultraviolet radiation from the sun broke the water molecules apart into hydrogen and oxygen. The light hydrogen atoms escaped into space, while the oxygen reacted with carbon in the rocks, which was then released into the atmosphere as carbon dioxide through volcanic activity. Without oceans to dissolve the carbon dioxide and lock it away in carbonate rocks, as happens on Earth, it accumulated in the atmosphere, creating the thick, suffocating blanket we see today. Venus is a stark warning for us. It shows how fragile the balance that keeps a planet habitable can be. It is a reminder of how dramatically a planet's climate can change when its delicate balance is disturbed by even a small change in its energy budget. And it is also a testament to how different the fates of two very similar planets can be when they evolve under slightly different conditions. When you look at that shining dot in the evening sky, remember that you are observing a world that could have been very similar to ours, but took a different, tragic path, a path that turned a potential paradise world into a hellish furnace where no terrestrial life can exist. Imagine if you could move away from Earth, past the orbit of the moon, and observe it from space. What would you see? A blue pearl suspended in the blackness of the cosmos, a swirl of white clouds and brown continents against a backdrop of deep blue oceans. It is a sight of breathtaking fragility and vibrancy, a living world in the vast, silent emptiness. Our planet is, in many ways, an anomaly, a precious exception in a solar system of extremes. It is the only place we know for certain that hosts life, a complex, interconnected web of biology that has transformed its surface, its oceans, and its atmosphere over billions of years. How is this possible? What confluence of factors makes our planet so special, a true habitable world? Let's start with its position, a factor of cosmic real estate. Earth orbits the Sun in the so-called habitable zone, a region sometimes referred to as the Goldilocks zone, where it is not too hot and not too cold for liquid water to exist on the surface. This is a crucial ingredient for life as we know it. Water is a remarkable molecule. Its ability to act as a universal solvent allows it to transport nutrients and facilitate the complex chemical reactions that are the basis of biology. On Earth, we have all three of its states: solid ice, liquid water, and gaseous vapor, which is unique in our solar system and allows for a dynamic water cycle that shapes our climate and ecosystems. But simply being in the habitable zone is not enough, as the fate of Venus demonstrates. Our atmosphere is another key element of our planet's habitability. It is a perfectly balanced, multi-layered shield, a thin, fragile bubble that separates us from the vacuum of space. Composed of 78% nitrogen, 21% oxygen, and trace amounts of other gases like argon and carbon dioxide, it provides the air we breathe, protects us from the sun's harmful ultraviolet radiation through its ozone layer, and maintains a relatively stable and pleasant temperature through a moderate greenhouse effect. The presence of so much free oxygen is itself a sign of life. Oxygen is a highly reactive element, and without its constant replenishment by photosynthetic organisms like plants and algae, it would quickly react with rocks and other elements and disappear from the atmosphere. The Great Oxidation Event, which occurred about 2.4 billion years ago, was a pivotal moment when early life fundamentally remade the chemistry of our planet. We cannot forget the Earth's magnetic field, an invisible guardian generated by the convection of molten iron in the planet's liquid outer core. This geodynamo creates a protective bubble around Earth called the magnetosphere, which extends thousands of kilometers into space. The magnetosphere deflects the solar wind, a constant stream of charged particles flowing from the sun. Without this shield, the solar wind would gradually strip away our atmosphere, as it did on Mars, and bombard the surface with lethal radiation. The interaction of the solar wind with the magnetosphere also creates the beautiful auroras, the northern and southern lights, a visible reminder of the cosmic forces at play. It is also interesting that we have an unusually large moon relative to the size of our planet. The moon's gravitational pull stabilizes the tilt of the Earth's axis, which is currently about 23.5 degrees. This stability ensures predictable seasons and prevents wild swings in climate that would occur if our planet wobbled erratically like a spinning top. The moon also causes the ocean tides, which create rich, dynamic intertidal zones that may have been crucial for the transition of life from the sea to the land. Our moon likely formed after a catastrophic collision between the young Earth and a Mars-sized protoplanet, an event that would have completely reshaped our world's early history and composition. Earth is also geologically active. Its surface is broken into tectonic plates that slowly move across the mantle, crashing into each other to form mountains, pulling apart to create new ocean floor, and subducting to recycle crust back into the interior. This process, the plate tectonic cycle, is vital for long-term climate stability. It is part of the carbonate-silicate cycle, which acts as a global thermostat. Volcanic activity releases carbon dioxide into the atmosphere, warming the planet, while the weathering of silicate rocks removes it, cooling the planet. This feedback loop has helped to keep Earth's climate relatively stable over geological timescales, despite changes in the sun's luminosity. And then there is the water itself. Over 70% of the Earth's surface is covered by oceans, which act as a massive heat reservoir, moderating global temperatures and driving weather patterns. The oceans provide a stable environment for a vast diversity of life and play a key role in the carbon cycle, absorbing a significant portion of the carbon dioxide we emit. All these factors, the right distance from the right kind of star, the right size, the right composition, the presence of a large moon, a magnetic field, plate tectonics, and abundant liquid water have come together to create a delicate and resilient system that has allowed for the existence of life in its astounding diversity. From microscopic bacteria in the deep-sea vents to the complex ecosystems of the rainforests, Earth pulses with life in all its corners. But this balance is not a given. It is the result of 4.5 billion years of coevolution between a planet and its biosphere, and it can be easily disrupted. When we look at our planetary neighbors, Venus and Mars, we see worlds that may have once resembled a young Earth, but their evolution took a different path. They are bookends to our own story, a reminder of how precious and fragile our blue-green home is in the vastness of the cosmos. The Red Planet, as Mars is often called, has always held a special place in the human imagination. Its distinct reddish hue, visible even to the naked eye as it wanders across the night sky, is reminiscent of blood and fire. It is no wonder that ancient civilizations, from the Babylonians to the Romans, named it after their gods of war for centuries. Mars has fueled fantasies about extraterrestrial life, from H.G. Wells's Invading Martians to Edgar Rice Burroughs' romantic tales of a dying world. The reality of Mars, as revealed by a fleet of robotic explorers, is just as fascinating, though different from these fantasies. It is a world of stark beauty and dramatic contrasts, a place that was once much more like Earth, and a prime target for our own future as a multiplanetary species. Mars is a world of superlatives. It is home to the highest mountain in the solar system, Olympus Mons, a colossal shield volcano that rises to a height of almost 27 kilometers, nearly 3 times the height of Mount Everest. Its base is so vast that it would cover the entire state of Arizona. It is also home to the deepest canyon, Valles Marineris, a system of canyons that stretches for over 4,000 kilometers along the Martian equator, dwarfing Earth's Grand Canyon. Mars itself is smaller than Earth. It has about half the diameter and only a tenth of its mass. Its gravity is just 38% of Earth's, which means you would weigh much less there and could leap 3 times as high. A day on Mars, known as a sol, lasts just a little longer than on Earth, at 24.7 hours. But a Martian year is almost twice as long, lasting 687 Earth days, leading to long, drawn-out seasons. When you look at the surface of Mars today, you see mostly a cold, dry, dusty wasteland. The atmosphere is incredibly thin, less than 1% the density of Earth's, and is composed mainly of carbon dioxide. The tenuous atmosphere provides little protection from solar radiation and is too thin to trap much heat. As a result, temperatures are extreme, ranging from a relatively pleasant 20 degrees Celsius on a summer day at the equator to a frigid minus 140 degrees Celsius at the poles during the winter night. But it was not always this way. There is now overwhelming evidence that Mars was once a much warmer and wetter world, a place far more similar to Earth. Robotic missions like the Spirit, Opportunity, Curiosity, and Perseverance rovers have discovered a wealth of geological evidence for a watery past. We have seen ancient river deltas, like the one at Jezero Crater being explored by Perseverance, dried up lake beds, and minerals that could only have formed in the presence of liquid water. There is evidence of massive outflow channels carved by catastrophic floods and possibly even the shoreline of a vast ancient ocean that may have covered much of the planet's northern hemisphere. So, where did all that water go? Some of it is still on Mars today, locked away as ice in the polar caps, which are a mix of water ice and frozen carbon dioxide, and as subsurface ice deposits. But most of it was likely lost to space. Unlike Earth, Mars does not have a global magnetic field to protect its atmosphere from the solar wind. While it may have had one in its early history, the planet's small size meant its core cooled and solidified faster than Earth's, and the protective geodynamo shut down. Over billions of years, the solar wind has been stripping away the Martian atmosphere, particle by particle. As the atmosphere thinned, the pressure dropped, and liquid water on the surface either evaporated or froze, leaving behind the cold, arid desert we see today. Nevertheless, Mars remains one of the most promising places in our solar system to search for traces of past life. If life ever arose on Mars during its warmer, wetter period, it could have left behind fossilized evidence in ancient lake sediments or other geological formations. The primary mission of the Perseverance rover is to collect rock samples from promising locations that a future mission could return to Earth for detailed analysis. It is even possible that microbial life could persist on Mars today, perhaps in subsurface brines or other protected niches where liquid water might still exist intermittently. Mars is also the most likely target for future human settlement. Its relative proximity to Earth, the presence of water ice, an atmosphere that could potentially be used to produce oxygen and rocket fuel, and relatively mild conditions compared to other planets make it the #1 candidate for creating the first extraterrestrial human colony. Imagine the day when humans walk on the red plains of Mars, look up at a pale pink sky, and watch 2 small, irregularly shaped moons, Phobos and Deimos, fly overhead It would be a monumental achievement, a new chapter in human history, transforming us from a single planet species into true citizens of the solar system. Beyond the asteroid belt, which forms a rocky demarcation line between the inner and outer solar system, lies the undisputed king of the planets, Jupiter. This gas giant is a true colossus, a world on a scale that is difficult to comprehend. It is more than twice as massive as all the other planets in our solar system combined. Over 1,300 Earths could fit inside its volume. Its presence has significantly influenced the evolution of the entire solar system, and it is sometimes described as a failed star, although it would need to be about 80 times more massive to ignite thermonuclear fusion in its core. Jupiter is a world of breathtaking beauty and violence, a swirling, dynamic canvas of atmospheric phenomena. When you look at Jupiter through a telescope, you are greeted by a stunning sight of alternating light and dark bands of clouds that encircle the planet. The light-colored bands are called zones, and the dark ones are called belts. These are formed by powerful jet streams blowing in opposite directions at speeds of up to 500 kilometers per hour. Driven by the planet's incredibly rapid rotation and the heat rising from its interior, Jupiter rotates faster than any other planet in our solar system. One day there lasts less than 10 hours. This rapid spin causes the planet to be visibly flattened at the poles and bulging at the equator, a shape known as an oblate spheroid. This rotation also contributes to the churning, chaotic weather patterns that dominate its atmosphere. The most prominent feature on Jupiter, its iconic emblem, is the Great Red Spot, a colossal anticyclonic storm that has been raging for at least 350 years, since astronomers like Robert Hooke and Giovanni Cassini first observed it with their primitive telescopes. This storm is so large that 2 or 3 Earths could fit inside it. It is a vast, high-pressure system, a hurricane whose winds at its edge reach speeds of over 600 kilometers per hour. Its deep red color is still a mystery, possibly caused by complex organic molecules or sulfur compounds being dredged up from deeper in the atmosphere and colored by solar ultraviolet radiation. The Great Red Spot is not alone. Jupiter's atmosphere is dotted with countless other storms and vortices, some white, some brown, creating a meteorological masterpiece. Jupiter does not have a solid surface like Earth. If you were to descend into its atmosphere, you would find yourself falling through progressively denser and hotter layers of clouds. First ammonia ice, then ammonium hydrosulfide, and finally water ice and vapor. The pressure and temperature would increase dramatically. At a certain depth, about 1,000 kilometers below the cloud tops, the pressure becomes so extreme, over 2 million times Earth's atmospheric pressure, that hydrogen, the main component of Jupiter's atmosphere, undergoes a phase transition. The electrons are squeezed out of the hydrogen atoms, and it begins to behave like a liquid metal, capable of conducting electricity. This vast ocean of metallic hydrogen is believed to be the source of Jupiter's immensely powerful magnetic field, which is nearly 20,000 times stronger than Earth's and creates a magnetosphere so large that if it were visible, it would appear larger than the full moon in our night sky. This magnetosphere traps charged particles from the solar wind, creating the most intense radiation belts in the solar system. These belts are so powerful that they would be lethal to an unprotected astronaut in minutes and pose a significant challenge for any spacecraft sent to study the planet. The interaction of these trapped particles with Jupiter's atmosphere also creates breathtaking auroras at its poles, far more energetic and extensive than those on Earth. Jupiter also plays an important role in our solar system as a kind of cosmic vacuum cleaner or gravitational shepherd. Its huge gravity has shaped the asteroid belt and has likely protected the inner planets, including Earth, from a more intense bombardment of comets and asteroids by either capturing them or ejecting them from the solar system. The most famous example of this protective effect was the collision of comet Shoemaker-Levy 9 with Jupiter in 1994. The comet was torn apart by Jupiter's gravity, and its fragments crashed into the planet's southern hemisphere, leaving behind a string of dark scars, some larger than the Earth, a dramatic reminder of Jupiter's role as our solar system's guardian. At least 95 moons are known to orbit Jupiter, forming a miniature solar system of their own. The 4 largest of these, the Galilean moons, were discovered by Galileo Galilei in 1610, a discovery that was instrumental in overthrowing the geocentric model of the universe. Each of these moons is a unique world worthy of separate study. Io is the most geologically active body in the solar system, its surface constantly repaved by hundreds of active volcanoes spewing sulfur and silicate lava, driven by the immense tidal forces from Jupiter's gravity. Europa, a world slightly smaller than our moon, is covered by a smooth, icy crust, beneath which lies a global ocean of liquid salt water, thought to contain more water than all of Earth's oceans combined. This subsurface ocean, kept liquid by tidal heating, is considered one of the most promising places in our solar system to search for extraterrestrial life. Ganymede is the largest moon in the solar system, larger even than the planet Mercury, and is the only moon known to have its own magnetic field. Callisto, the outermost of the Galilean moons, is a heavily cratered, ancient world, its surface a frozen record of the history of the early solar system. Jupiter and its family of moons represent a system of incredible complexity and diversity, a laboratory for studying planetary science and a prime target in our quest to understand the potential for life beyond Earth. When Galileo Galilei first pointed his simple telescope at Saturn in 1610, he was confused by what he saw. The planet appeared to have two ears, or handles, on its sides, strange appendages that he could not explain. It was not until 45 years later that the Dutch astronomer Christian Huygens, with a more powerful telescope, correctly determined that these formations were actually a system of rings surrounding the planet, a flat, thin disk that was not touching it. Today, we know that Saturn is adorned with the most beautiful and extensive system of rings in the solar system, a feature of such elegance and complexity that it makes the planet a true jewel of the cosmos. Saturn is the second largest planet in our solar system, after Jupiter, and like its larger neighbor, it is a gas giant composed mainly of hydrogen and helium. However, Saturn is much less dense. In fact, its average density is lower than that of water. If you could find an ocean large enough, Saturn would float in it. It is the only planet in our solar system with this property. At first glance, Saturn's atmosphere resembles Jupiter's, with bands of clouds encircling the planet, but its colors are more subdued, in pastel shades of yellow, gold, and beige, due to a thicker haze layer in its upper atmosphere. The winds on Saturn are among the fastest in the solar system, reaching speeds of up to 1,800 kilometers per hour at the equator. At Saturn's North Pole, the Cassini spacecraft discovered a bizarre and mesmerizing feature, a stable, hexagonal jet stream, a cloud pattern with 6 straight sides, each side wider than the Earth. The origin of this geometrically perfect formation is still being studied, but it is thought to be a standing wave pattern in the planet's atmospheric currents. But what truly sets Saturn apart are its magnificent rings. They extend from about 7,000 to 120,000 kilometers above the planet's equator, yet their thickness is astonishingly small, in most places only a few tens of meters. They are composed of billions of particles of almost pure water ice, ranging in size from microscopic dust grains to boulders the size of houses. These particles orbit the planet at incredible speeds, creating a complex and dynamic structure with thousands of individual ringlets, gaps, and density waves, sculpted by the gravitational influence of Saturn's many moons. The major rings are labeled with letters in the order of their discovery. The brightest and most prominent are the A and B rings, which are separated by the Cassini division, a gap about 4,800 kilometers wide that is visible even in amateur telescopes. The origin of the rings has long been a mystery. They could have formed from the breakup of a moon or a captured comet that came too close to Saturn and was torn apart by its immense tidal forces, a region known as the Roche limit. Or they could be the primordial remnants of the material from the nebula from which Saturn itself formed, material that never managed to coalesce into a moon. Data from the Cassini mission surprisingly suggested that the rings are relatively young, perhaps only 100 million years old, meaning they may have formed during the age of the dinosaurs on Earth. This finding is still debated, but it suggests that planetary rings may be a transient, rather than a permanent, feature. Saturn also has a rich and diverse family of at least 83 known moons, ranging from small, irregularly shaped rocky bodies to giant worlds. The largest of these, Titan, is a world of extraordinary interest. It is larger than the planet Mercury and is the only moon in the solar system with a dense, substantial atmosphere, even denser than Earth's. Titan's atmosphere is composed mainly of nitrogen, like our own, but it also contains methane and other organic compounds. The conditions on Titan are so cold, around minus 180 degrees Celsius, that methane can exist as a liquid, solid, and gas, playing a role similar to water on Earth. The Cassini-Huygens mission revealed a stunning landscape on Titan, with rivers, lakes, and seas of liquid methane and ethane, making it the only body besides Earth that we know of that has stable liquid on its surface. It is a strange, alien version of our own world, a place where it rains methane and the riverbeds are carved by liquid hydrocarbons. Another of Saturn's moons, the small, icy Enceladus, has turned out to be one of the most exciting places in the solar system. Despite its small size, it is geologically active. The Cassini spacecraft discovered huge geysers erupting from cracks near its south pole, spewing plumes of water vapor, ice crystals, and organic molecules into space. This discovery is strong evidence for a global ocean of liquid water lurking beneath its icy crust, kept warm by tidal heating from Saturn's gravity. The presence of liquid water, organic molecules, and a source of energy makes Enceladus a prime candidate in the search for extraterrestrial life. When you look at Saturn through a telescope, you are not just seeing a beautiful object. You are observing a complex and dynamic system, a world of incredible storms, ephemeral rings, and moons that could potentially harbor life, a true gem of our solar system. Far beyond the orbit of Saturn, in the cold, dim outer regions of our solar system, lie two worlds that are significantly different from the other planets. Uranus and Neptune are often referred to as ice giants, a distinct class of planet from the gas giants Jupiter and Saturn. While Jupiter and Saturn are composed almost entirely of hydrogen and helium, Uranus and Neptune are made up of a much higher proportion of heavier elements, or ices, such as water, ammonia, and methane. These materials are not frozen solid in the way we think of ice on Earth. In the planet's interiors, under extreme pressures and temperatures, they form a hot, dense, electrically conductive fluid, a kind of supercritical ocean surrounding a small, rocky core. Uranus was the first planet to be discovered with a telescope. In 1781, the British astronomer William Herschel was systematically scanning the sky when he spotted a faint object that he initially thought was a comet. After further observation, it became clear that it was a new planet, the first to be discovered since antiquity, doubling the known size of the solar system. Uranus is the third largest planet by diameter and the fourth most massive. On a clear, dark night, under ideal conditions, it is just at the edge of visibility for the naked eye. But its faintness and slow movement across the sky meant it was overlooked for millennia. The most remarkable and bizarre feature of Uranus is its extreme axial tilt. While other planets spin more or less upright as they orbit the Sun, like spinning tops, Uranus is tilted on its side, with its axis of rotation lying almost in the plane of its orbit, at an angle of nearly 98 degrees. This means that it essentially rolls along its orbital path. This extreme tilt leads to the most extreme seasons in the solar system. During its 84 Earth-year orbit, each pole gets 42 years of continuous sunlight, followed by 42 years of continuous darkness. The reason for this peculiar orientation is thought to be a cataclysmic collision with an Earth-sized protoplanet during the chaotic early history of the solar system. Such a massive impact would have been powerful enough to knock the young planet over on its side. Uranus has a faint system of dark rings, discovered in 1977, and is orbited by 27 known moons, which are uniquely named after characters from the works of William Shakespeare and Alexander Pope. Rather than from Greek or Roman mythology, Neptune, the last of the major planets, has a discovery story that is a triumph of theoretical physics. After the discovery of Uranus, astronomers noticed that its orbit was not quite what Newton's laws of gravity predicted. There were slight perturbations, suggesting that the gravity of an unknown, more distant planet was tugging on it. In the 1840s, two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently used these perturbations to calculate the position of the hypothetical planet. In 1846, Le Verrier sent his prediction to the Berlin Observatory, And on the very first night of searching, the astronomer Johann Galle found Neptune within 1 degree of the predicted position. It was a stunning confirmation of the power of Newtonian physics. Neptune is the smallest of the giant planets, but it is denser than Uranus and has a stronger gravitational pull. It is also the coldest of the major planets, with cloud-top temperatures dropping into around -220 degrees Celsius. Despite this, and despite receiving only a tiny fraction of the sunlight that Jupiter does, Neptune's atmosphere is surprisingly dynamic and turbulent. When the Voyager 2 spacecraft flew by Neptune in 1989, it captured images of the Great Dark Spot, a huge storm system similar to the Great Red Spot on Jupiter. The most remarkable feature of Neptune's atmosphere, however, is its winds. The fastest winds in the solar system have been recorded on Neptune, reaching supersonic speeds of up to 2,100 kilometers per hour. The source of the internal heat that drives this extreme weather is still a mystery. Neptune also has a faint, clumpy ring system and is orbited by 14 known moons. The largest of these, Triton, is one of the most fascinating bodies in the solar system. It is a large, icy moon that orbits Neptune in a retrograde direction, opposite to the planet's rotation. This is strong evidence that Triton was not formed with Neptune, but is a captured object from the Kuiper Belt, a vast reservoir of icy bodies beyond the orbit of Neptune. Triton is geologically active, with geysers of nitrogen gas and dust erupting from its surface. And it has a very thin nitrogen atmosphere. Its capture by Neptune would have been a chaotic and violent event, likely destroying Neptune's original system of moons. For almost 8 decades, Pluto was considered the 9th planet in our solar system, a small, icy world at the dim frontiers of our planetary system. It was discovered by the American astronomer Clyde Tombaugh in 1930 at the Lowell Observatory in Arizona, after a painstaking search for a predicted Planet X beyond Neptune for generations. Pluto was the final, mysterious outpost in our solar system. But in the late 20th and early 21st centuries, astronomers began to discover other objects in the outer solar system, in a region called the Kuiper Belt, that were similar in size to Pluto, such as Eris, which was initially thought to be even larger. This raised a problem if Pluto was a planet. Should all these other new objects be planets too? The question came to a head in 2006, when the International Astronomical Union met in Prague and, after a stormy debate, adopted a formal definition of a planet for the first time. According to this new definition, a celestial body must meet 3 criteria to be called a planet. It must orbit the Sun. It must be massive enough for its own gravity to pull it into a nearly round, or hydrostatic equilibrium, shape, and it must have cleared the neighborhood around its orbit, meaning it has become gravitationally dominant, with no other bodies of comparable size other than its own satellites. It was this third condition that proved fatal for Pluto. Pluto orbits in the crowded Kuiper Belt and has not cleared its orbital zone. Therefore, it was reclassified as a dwarf planet, a new category of objects that meet the first 2 criteria, but not the third. This decision sparked not only a scientific debate, but also an emotional reaction from the public. Many people who grew up learning about 9 planets have not accepted this change to this day. But, while Pluto may have lost its planetary status, it has gained so much more in our understanding. In 2015, NASA's New Horizons probe, which was launched the same year Pluto was demoted, performed the first ever flyby of this distant world, sending back images that exceeded all expectations. Instead of a dead, inert ball of ice and rock, New Horizons revealed a surprisingly complex and geologically active world. On the surface of Pluto, we discovered a vast, bright, heart-shaped region named Tombaugh Regio, which is a massive glacier of frozen nitrogen. We found towering mountain ranges made of water ice, which at Pluto's frigid temperatures of around -230 degrees Celsius, is as hard as rock. We found evidence of flowing nitrogen ice glaciers, a thin, hazy nitrogen atmosphere, and possible cryovolcanoes that may have erupted a slushy mixture of water, ammonia, and methane. This level of geological activity was completely unexpected on such a small, cold world, suggesting that Pluto may have a source of internal heat, perhaps from the radioactive decay of elements in its core, or a subsurface ocean of liquid water. New Horizons also studied Pluto's largest moon, Charon, which is so large in proportion to Pluto, about half its diameter, that they are better described as a binary system, orbiting a common center of gravity that lies in the space between them. Charon also has a fascinating and varied geology, including a huge canyon system that dwarfs the Grand Canyon on Earth. The flyby of Pluto and Charon transformed them from distant, fuzzy points of light into vibrant, complex worlds, the best explored objects in the Kuiper Belt. Pluto's story is a powerful reminder that our classifications are human constructs, and that the universe is full of wonders that defy our neat and tidy categories. For millennia, people only knew about the planets of our own solar system. Philosophers and scientists speculated whether planets orbit other stars, but they had no way of proving it. This changed forever in 1995, when Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of the first planet orbiting a sun-like star outside our solar system. This planet, named 51 Pegasi b, started a revolution in astronomy, opening a new window onto the cosmos. Today, 3 decades later, we know of more than 5,000 confirmed exoplanets, and their number is growing almost daily. These distant worlds are incredibly diverse and often very different from the planets of our solar system. Their discovery has shown us that our solar system is just one of many possible configurations, and that the universe is filled with planetary systems that defy our imagination. The detection of exoplanets is an extraordinary technical challenge. They are incredibly faint compared to their parent stars and are located at immense distances, making them impossible to see directly with most telescopes. It is like trying to spot a firefly next to a brilliant searchlight from hundreds of miles away. To find these hidden worlds, astronomers have developed a suite of clever indirect methods. The most successful of these are the radial velocity method and the transit method. The radial velocity method, which found 51 Pegasi b, takes advantage of the fact that a planet and a star orbit a common center of gravity. As a planet orbits its star, it causes the star to wobble slightly back and forth. We can detect this wobble by observing the star's light. As the star moves toward us, its light is slightly shifted to the blue end of the spectrum, and as it moves away, it is shifted to the red end. This tiny periodic Doppler shift in the star's light reveals the presence of an unseen companion and allows us to estimate its mass. The transit method, which has been responsible for the vast majority of exoplanet discoveries thanks to missions like the Kepler Space Telescope, consists of monitoring the brightness of a star over time. If a planet passes in front of its star from our perspective, an event known as a transit, it will block a tiny fraction of the starlight, causing a slight periodic dip in the star's brightness. This method allows us to determine the planet's size and its orbital period. By combining the transit and radial velocity methods, we can determine a planet's density, which gives us our first clue about its composition. Other methods include gravitational microlensing, which uses the gravity of a star or planet to magnify the light of a more distant star, a technique particularly good at finding free-floating planets, and direct imaging, which involves blocking out the light of a star with a special instrument called a coronagraph to directly see the faint light of the planets orbiting it. This last method is extremely difficult, but has been successful in a few cases, giving us our first direct pictures of other worlds. The first discovered exoplanets were mostly so-called hot Jupiters, massive gas giants orbiting extremely close to their stars. This was not because they are the most common type of planet, but because they are the easiest to detect. Their large mass creates a strong gravitational tug, making them easy to find with the radial velocity method, and their large size and short orbital periods mean they cause frequent and deep transits. These strange worlds orbit their stars at extreme proximities, often closer than Mercury is to the Sun, completing one orbit in a few days or even hours. Their atmospheres are heated to thousands of degrees, and some are so close that they are being stripped away by their star's radiation, creating long, comet-like tails of gas. As our technologies improved, we began to discover smaller and more distant planets as well. The Kepler Space Telescope, launched in 2009, was a game changer. By staring at a single patch of sky in the constellation Cygnus for 4 years, it monitored the brightness of over 150,000 stars, discovering thousands of exoplanets and revealing the statistical prevalence of planets in our galaxy. Kepler's data showed us that planets are incredibly common. On average, there is at least one planet for every star in the Milky Way, which means there could be hundreds of billions of planets in our galaxy alone. One of the most surprising findings from Kepler was that the most common type of planet in our galaxy are those that we do not have in our solar system at all. Super-Earths, planets larger than Earth but smaller than Neptune, and mini-Neptunes, or gas dwarfs, which fall in the size range between Earth and Neptune. The existence of these common types of planets, and their absence in our own solar system, is a major puzzle in planetary science and suggests that our solar system's architecture may be somewhat unusual. The search for exoplanets is not just about cataloging other worlds, it is about understanding our own place in the universe. Each newly discovered planet is another piece of a puzzle that helps us refine our theories of how planets form and evolve. It pushes us to expand our understanding of what is possible, from the fiery hellscapes of lava worlds to the frozen darkness of rogue planets. And, most profoundly, it brings us closer to answering one of humanity's oldest and most fundamental questions: are we alone? The search for Earth-like planets in the habitable zones of their stars, worlds where life as we know it could potentially exist, is now at the forefront of astronomical research, a quest that could change our perception of the universe forever. As we continue to explore the galactic neighborhood, a recurring theme emerges: the sheer, unbridled diversity of worlds. The more exoplanets we discover, the more clearly we see that our own solar system, once the only template we had, is not a typical example of a planetary system. The universe is a far more creative and chaotic architect than we had imagined. One of the most striking findings is that the most common types of planets in our galaxy are those that are conspicuously absent from our own celestial family, the so-called super-Earths and mini-Neptunes. Super-Earths are a class of planets with a mass between that of Earth and Neptune, typically between 1 and 10 times the mass of our own planet. As the name suggests, they are larger than Earth but are thought to be primarily rocky, at least at the lower end of their mass range. It is important to understand that the term super-Earth describes only the planet's size, not its composition or habitability. Some super-Earths may indeed be scaled-up versions of our world, with a solid surface, a thin atmosphere, and potentially liquid water. An example of a potentially rocky super-Earth is Kepler 452b, sometimes dubbed Earth's cousin, which is about 60% larger than Earth and orbits in the habitable zone of a sun-like star. Others, however, could be very different. They might be water worlds, planets with a small rocky core covered by a deep global ocean, or they could have thick, hydrogen-dominated atmospheres that would make their surfaces crushingly hot and uninhabitable. Mini-Neptunes, sometimes called gas dwarfs, are planets that are smaller and less massive than our own ice giants, Uranus and Neptune, but still have a substantial gaseous envelope. They typically have a mass between 10 and 50 times that of Earth. These worlds likely have a large rocky or icy core surrounded by a thick atmosphere of hydrogen, helium, and other volatile gases. A typical example is Kepler 11f, which has a diameter about 2.5 times that of Earth, but is much less dense, suggesting it is not a rocky world, but has a significant atmosphere. The distinction between a large super-Earth and a small mini-Neptune is blurry, and there is likely a continuum of planets between these two categories. The fact that these intermediate-sized planets are so common in the galaxy, yet missing from our solar system, is a profound puzzle. Our solar system has a clear gap. The largest rocky planet is Earth, and the smallest giant planet is Neptune, which is about 17 times more massive than Earth. There is nothing in between. Why? The answer may lie in the chaotic history of our solar system's formation. One leading theory, the Grand Tack hypothesis, suggests that Jupiter, in the early days of the solar system, migrated inward from its formation location, coming as close to the Sun as the orbit of Mars, before being pulled back outward by the gravitational influence of Saturn. This inward and outward journey would have acted like a giant snowplow, disrupting the orbits of the planetesimals and protoplanets in the inner solar system and potentially clearing out the material that would have otherwise formed super-Earths. In this view, Our solar system's architecture is a direct result of the specific dance of our giant planets. The existence of super-Earths and mini-Neptunes also forces us to rethink our understanding of planet formation. Traditional models, developed based on our solar system, have had difficulty explaining the existence of these intermediate types of planets. Newer models, which take into account the migration of planets through the protoplanetary disk and the complex interactions between growing planets, are beginning to offer a better explanation for the observed diversity. The study of these common but alien worlds provides us with valuable insight into the processes that shape planetary systems across the galaxy. It also helps us to better understand how exceptional or common our own Earth may be. Perhaps the very architecture that prevented the formation of super-Earths in our solar system was a key factor that allowed for the long-term stability and habitability of our own planet. The diversity of worlds extends far beyond their size. We have found planets with extreme densities. PSR J179-1438b is a planet orbiting a rapidly spinning neutron star, a pulsar. It is so dense that scientists believe it may be the crystalline core of an ancient white dwarf star, composed mainly of carbon and oxygen that has been compressed into a planet-sized diamond. On the other end of the spectrum are the super puffs, planets with the density of cotton candy. Kepler 51b, for example, is a Jupiter-sized planet but has only a tiny fraction of its mass, making it one of the lowest density planets ever discovered. Then there are the planets with the most bizarre orbits. HD 80606b has one of the most eccentric, or elongated, orbits we know of. It spends most of its 111-day year far from its star, in a cold, distant region, but then it swings in on a close, scorching pass, causing extreme and rapid temperature changes. The exoplanet TRES 2b is one of the darkest worlds known, reflecting less than 1% of the light that falls on it, making it darker than coal or black acrylic paint. Its atmosphere is thought to contain light-absorbing chemicals like vaporized sodium and potassium. These extreme worlds remind us how diverse and wondrous the universe around us is. They are natural laboratories for testing our understanding of physics under conditions that we could never replicate on Earth. They show us that nature's imagination is far more vast than our own, and they highlight the extraordinary and perhaps rare combination of factors that have made our own planet a stable, temperate, and life-bearing world. When we look at the night sky, we can now imagine that around each of those distant stars orbit worlds that are more different from our own planets than we could have ever conceived. The universe is not just a collection of familiar objects. It is a veritable zoo of cosmic oddities, each one with its own unique story to tell. When we search for the possibility of life beyond Earth, we naturally focus on planets that could have conditions similar to our own home world. A key concept in this search is the so-called habitable zone, a term often used in popular science, but one that is more complex than it might seem. It is traditionally defined as the region around a star where the temperature is just right for liquid water to exist on the surface of a rocky planet with a suitable atmosphere. It is sometimes called the Goldilocks zone, not too hot, not too cold, but just right. The importance of liquid water for life as we know it cannot be overstated. It is a superb solvent, allowing the complex molecules of life to dissolve and interact. It has a high heat capacity, which helps to moderate temperatures, and its solid form, ice, is less dense than its liquid form, which means that lakes and oceans freeze from the top down, insulating the liquid water below. It is no wonder that in the search for life, the mantra of astrobiologists has long been "follow the water." The position and width of the habitable zone depend critically on the type of star, around hot, bright, massive stars. The habitable zone is farther out and wider, around cooler, fainter, less massive stars, like red dwarfs. It is much closer to the star and narrower. Our own sun is a G-type star, and its habitable zone is generally considered to extend from somewhere inside the orbit of Venus to just outside the orbit of Mars, with Earth nestled comfortably in the middle. But simply being in the habitable zone is no guarantee of habitability. A planet's ability to support life depends on a host of other factors. The size of the planet is crucial. If it is too small, like Mars, It will have difficulty holding on to a substantial atmosphere and may cool down too quickly, losing its geological activity. If it is too large, it may become a mini Neptune, with a thick, crushing atmosphere unsuitable for surface life. The planet's composition, the presence of a magnetic field to shield it from stellar radiation, and the existence of plate tectonics to regulate its climate over long timescales are all thought to be important factors. The star itself is also a major consideration. While red dwarfs are the most common type of star in the galaxy, and many have been found to host Earth-sized planets in their habitable zones, they also pose significant challenges. They are known for their intense stellar flares, which could strip away the atmospheres of close-in planets and bathe their surfaces in lethal radiation. Also, planets in the habitable zone of a red dwarf are so close to the star that they are likely to be tidally locked, with one side in perpetual daylight and the other in perpetual darkness, creating extreme temperature contrasts. G-type stars like our Sun, or slightly cooler K-type stars, are often considered better candidates for hosting life, as they are more stable and have a longer lifespan. Among the most promising candidates for habitable exoplanets discovered so far is Proxima Centauri b, which orbits the nearest star to our Sun at a distance of only 4.2 light-years. It is a rocky planet only slightly more massive than Earth and orbits within its star's habitable zone. However, its star is an active red dwarf, raising questions about its true habitability. Another exciting system is TRAPPIST-1, located about 40 light-years away. It is an ultra-cool red dwarf orbited by 7 Earth-sized rocky planets. At least 3 of these planets, TRAPPIST-1e, F, and G, are in the habitable zone. TRAPPIST-1e is perhaps the most intriguing, with a size and density very similar to Earth's. The James Webb Space Telescope is currently studying the atmospheres of these planets, searching for clues about their composition and potential for hosting life. Kepler-186f was the first Earth-sized planet discovered in the habitable zone of another star. It is about 10% larger than Earth and orbits a red dwarf star about 500 light-years away. The concept of habitability is also expanding beyond the traditional habitable zone. The moons of giant planets, like Europa and Enceladus in our own solar system, could have subsurface oceans of liquid water, kept warm by tidal heating, far outside the Sun's habitable zone. This raises the possibility that habitable moons could be common throughout the galaxy. A special category of potentially habitable worlds are ocean planets, or Hycean worlds, planets that have much more water than Earth, and whose surfaces are entirely or mostly covered by a global ocean. These planets could have a wide range of habitable conditions, and some may have hydrogen-rich atmospheres. Life in such worlds would be purely aquatic and could be very different from life on Earth. As we discover more and more exoplanets and improve our methods of analyzing their atmospheres and surfaces, we are moving from simply cataloging other worlds to characterizing them in detail. The search for a second Earth is not just about finding a twin of our own planet. It is about understanding the full range of conditions under which life might be able to arise and thrive in the universe. It is a quest that may, in the coming decades, provide us with one of the most profound answers in the history of science. Our journey through the cosmos has revealed a universe brimming with worlds, a place of far greater diversity and strangeness than our ancestors could ever have dreamed. From the scorched, cratered plains of Mercury to the frozen, distant plains of Pluto, from the swirling storms of Jupiter to the methane seas of Titan, our own solar system is a testament to the varied outcomes of planetary formation. But it is in the realm of exoplanets that the true, bewildering diversity of the universe is revealed. We have found planets that defy our neat classifications and challenge our understanding of what a planet can be. There are hot Jupiters locked in a fiery embrace with their stars, super-Earths that may be scaled-up versions of our own world, and mini-Neptunes that fill a gap in our own solar system's architecture. There are diamond planets, lava worlds, and planets where it rains glass sideways and supersonic winds. There are lonely, wandering planets, cast out from their home systems to drift through the interstellar darkness, and planets that dance a complex waltz around two suns. Each new discovery is like another piece of a grand puzzle, helping us to build a more complete picture of how planets form and evolve. But perhaps the most important question that drives our exploration of these distant worlds is the oldest and most profound of all: are we alone? As we have seen, there are many worlds that could, in principle, have the right conditions for life as we know it. The subsurface oceans of moons like Europa and Enceladus, the ancient riverbeds of Mars where water once flowed, and the many exoplanets found orbiting in the habitable zones of their stars all represent tantalizing possibilities. The sheer number of potentially habitable worlds in our galaxy, perhaps tens of billions of them, suggests that the raw ingredients for life may be common. If life is common, what might it look like? Perhaps it would be microbial, simple organisms thriving in niches protected from the harshness of space. Or perhaps, on some worlds, it has had the time to evolve into complex, multicellular forms, creating ecosystems as rich and diverse as our own. It could be based on the same carbon chemistry and water solvent as life on Earth, or it could be based on completely different principles, a truly alien biology that we can currently only speculate about. Life could exist in the liquid methane of Titan's seas, in the dense atmospheres of gas giants, or even as a form of silicon-based life on a hotter world. The possibilities are as vast as the universe itself. But even non-living worlds offer us fascinating insights. They are natural laboratories where we can study physics under extreme conditions. The volcanic activity on Io, driven by tidal forces, teaches us about geology and heat transfer. The rings of Saturn provide a miniature model for the dynamics of protoplanetary disks. The extreme weather on Neptune challenges our models of atmospheric physics. By studying these other worlds, we learn more about the fundamental laws that govern our universe. What does the future hold for our exploration of these cosmic neighbors with new and more powerful telescopes, like the James Webb Space Telescope and future ground-based observatories? We will be able to probe the atmospheres of more and more exoplanets, searching for the telltale chemical fingerprints of life, or biosignatures. Missions are being planned to return to the ocean worlds of our outer solar system, to land on Europa's ice and perhaps even drill down to its hidden ocean. And humanity is taking its first tentative steps towards becoming a multiplanetary species, with Mars as our first destination. But whatever we discover, one thing is certain: the universe will always be larger, more complex, and more wondrous than we can imagine. Every new answer will bring with it a host of new questions, revealing ever deeper layers of mystery and beauty. As Carl Sagan so eloquently put it, we are a way for the cosmos to know itself. We are the product of cosmic evolution, stardust that has become conscious. In our quest to explore other worlds, we are not just looking outward, we are also looking inward, seeking to understand our own origins and our place in the grand cosmic scheme. So the next time you look up at the night sky, remember that what you see are not just distant points of light, they are other suns, each one a potential center of its own system of worlds, a system that could be as familiar as our own or as alien as our wildest dreams. And somewhere out there, there may be other beings looking up at their own sky and asking the same questions. In this endless dance of cosmic dust and energy, in the constant cycle of the birth and death of stars and planets, we are part of something immensely large and beautiful, children of the stars, and perhaps, one day, we will become citizens of the cosmos.